Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. We are going through the central processing unit design. We defined the instruction set architecture and took some examples of sample processors. We illustrated the data path and its implementation. Then we also saw some advanced features in the case of a design of computer architecture like pipelining. Then we said control unit is an important part of the CPU design. The control unit needs to activate and generate the control signals for different hardware components like registers or to activate the tri-state buffers. Now the control signals for the control unit could principally be generated in two ways, either using a hardwired approach or we could use microprogramming. In the last lecture, we discussed in detail how the microcode for a microprogramming could be generated. Comparing these two techniques, that is the hardwired and the microprogramming technique, we just saw that the hardwired approach usually is faster. However, the microprogramming gives us more flexibility, and in the process of development or prototyping, this could be a useful technique. In the earlier days, when the memories were slow, in that case, and hardware was not so well developed, the microprogramming was quite popular. With the advent and advancement of the programmable logic arrays, now the hardware techniques also provides an equally good flexible approach, and this could give a faster solution to control the generate signals. Now whether we use one technique or the other technique, the control unit needs to provide appropriate control signals at appropriate timing intervals. Now from the main clock generator, we generate different timing steps. For example, 8 timing steps, T0 up to T7, and depending upon which particular instruction is being executed, we saw how to write the structural RTL for each case, and then depending upon the data path, how to activate the data and the control signals. Now, the second important part which we have still assumed is the arithmetic logic shift unit in a CPU. ALSU, as we said, is primarily a combinational circuit. So inside the ALSU, primarily we would have the adders, AND, OR, NOT, and different gates combined together with the hard logic, and we would be able to implement the addition process, subtraction, multiplication, division, and shift, and OR, and all these different processes. So till now in our representation, we had considered the ALSU as a black box, and the black box at the input has got two operands. We just called operand A and operand B, and the output we just named arbitrarily as C. And then we had the control signal. Depending upon which particular instruction is being implemented, this control signal could be like add or subtract, and or shift left, shift right, and other operations depending upon which particular processor is being talked about. It could be SRC or Falcon, which we have discussed earlier. For the implementation of ALSU today, we will just go in somewhat more detail and see how different operations are implemented using the hardware and software combination. Theoretically, you could say that everything could be done in software with certain standard registers and then data transfer. From the very first lecture, you could imagine that we said we could have accumulator-based architecture or stack-based architecture, and there could be ways and means where you could have different operations. But doing it in hardware would be usually faster. So providing this ALSU as a hardware unit in a combinational circuit form would facilitate and give us a better provision for efficient operations or a better, faster operations from ALSU. Now, for proper understanding of the ALSU, we need to understand the basics of representation of numbers. For example, the designer needs to specify how many bits would be there for the operand, how many bits would be provided for the result, and then what is the largest number, and if there is, for example, multiplication, could there be a truncation error, could there be overflows, all these aspects have to be looked into. Now, before we can just go to the actual design of ALSU, we need to understand some simple concepts regarding representation of numbers. Now, although this could be a review of what you have done in your earlier courses, still it is necessary that we go through this review and we'll try to formalize certain mathematical representations. This could be what you have already done, but still it is important that we review it with reference to ALSU unit. Now, one important question before we go to the actual mathematical representation. What is the radix which is normally used? The base of the numbers which we are going to talk. Now, usually you know that in the case of CPU or the processors, our standard base is 2, and the human beings are using a base 10. Now, conversion from base 2 to base 10 and vice versa is quite evident, and it could be done quite conveniently, but we could generalize it for any particular base. We will call one base as B, and that is for hand calculations or for human beings. And we will use just the notation C for the base corresponding to the computer, or it could be, let us say, a normal calculator. So in your book, it is just mentioned as the calculator base, and the second one is base B. Now, B could be larger, C could be larger, there could be different conditions, but typically we could say B could be 10 and the C could be either 2 or it could be octal. For octal it would be 8. For hexadecimal it would be 16. Now, whatever is the case, the formulae which we are going to write and which you will see in the slides would be primarily independent of what are the values of B and C. So, representation of these numbers could be in decimal with numerals from 0 to 9. If it was binary, we will just write 0 and 1. For hexadecimal, we go from 0 up to F, and the decimal is a subset of the hexadecimal. So we see in our next slide how to convert the base, the radix conversion from one base to the other. Let us look into a couple of simple examples. The conversion between different number systems can be implemented in software or hardware. The block diagram shown in this slide illustrates the algorithm, which could be implemented either using hardware or through software. We have to start with a number represented in base b, and we write it with coefficients x0, x1 up to xm minus 1. That means there are m positions for representing this number. Now we initialize for base c the value which we call x to 0, and that is the starting point. Then we fetch the next coefficient xi, working from left to right. That means the first one which we are going to fetch would be xm minus 1, and the last one would be x0. After obtaining xi in base b, we convert to the number di having base c, and this could be very conveniently done by using a lookup table. Now, this lookup table may not be explicitly written for you, that you might have in mind. As an example, if our base b is hex, then we have numbers from 0 up to f, and if the base c is decimal from 0 to 9, we have the same numerals. A would be written as 10, b as 11, and f correspondingly would be 15. So we convert the number with coefficient xi from base b to its equivalent value di using base c. Now then we update the value with base c by writing x equal to x multiplied with value of base b and add to this di. Now then we repeat for all the digits right from m minus 1 going up to 0. So through this cycle we get the final value of the corresponding equivalent number in base c. Let us have a look at the simple worked example. A simple example gives us the conversion from hexadecimal number b3 to equivalent base 10. According to this algorithm, we put x equal to 0, we initialize it to 0, then the next value of x is x plus what is b in this case, the digit on the leftmost position, and decimal value is 11 from the table. So the value of x in first step becomes 11. Then we multiply this 11 with the base, which is 16. So 16 times 11, and we add the next digit read as 3 in this case. So it would be 179. Therefore, the equivalent decimal value would be 179 with base 10. Now the conversion in the reverse direction is also possible, and that is shown in the next slide. So we convert from the calculator or computer's base, which we call it c, to the base b, which is as an interface base for human beings, typically the decimal. Now we start with base c integer, initialize with I equal to 0, and the value we call it v equal to x, and now we produce the digits from right to left. It's just opposite to what we had in the previous table. Now set the value of di as v modulus b. That means divide v by b, and whatever is the remainder, that would be the value of di. And at the same time, the v becomes V divided by B, and this symbol indicates the floor operator, which would mean actually we are interested in quotient, and we'll get two values after conversion. One is the quotient that we put as V, and the remainder we take the coefficient, and that would be the base xi, which is from B converted to di with c. Now we just go to the next step and repeat with I equal to I plus 1, and if V is not equal to 0, we repeat till we come to the last digit. Let us look at this example. Convert 390 in decimal to base 16 hexadecimal base. So C is 10 and B is 16. According to the simple algorithm, we divide 390 by 16 and we get 24 with a residue 6. So the coefficient x naught becomes 6. Then the new value of B is 24. We again divide it by 16. We get 1 and remainder is 8. So the next coefficient is 8, which is x1. And 1 again divided by 16, it is 0 and remainder is 1. So the final value x2 is equal to 1. So written in the form of hexadecimal, we will get 186 in hex. So therefore 390 with base 10 is equal to 186 to base 16. Now fixed point representation of numbers, we say we have a number with a radix point, and if it is decimal, we call it a decimal point. For example, 16.12. We say that there are 2 digits on left side of the decimal and 2 digits in this example on the right side of the decimal. Now if we have the position of this radix, which could be decimal for the case of decimal representation, is fixed, we call it a fixed point representation. Just for example, if we have an integer, then this radix point would be on the rightmost. On the other hand, if it is a fraction, then the radix point would be on the leftmost, like 0.16, then we have the radix point on the left. 16.0, and if we write 0.0 or not 16, the decimal point in this case is understood to be on the rightmost. Now there could be situations where we could shift the position of this radix. So if we shift it left or right, that would correspond to scaling, and we could have this as a multiplication with a base or division by this base. As an example, if we have a decimal number and we write 120.0 and we left this decimal point on our left, we divide it by 10. This would be 12 in this case. On the other hand, if I take 120.0 and I shift the decimal on the right, this would become 1200 and it would be equivalent to multiplication with 10. And if it was a hexadecimal number, it would correspondingly imply a multiplication or a division by 16 when we shift this point to left or right. So this would be a scaling operation, and you remember in one of the SRC operations, when we shift arithmetic shift left or right, we implemented an algorithm for multiplication with a power of 2 or division by a power of 2. It could be division, but in SRC, in Falcon, we had this multiply and divide instructions. It was not there in SRC processor. Now let us have another example of an unsigned fraction for base conversion. we convert from base B to a computer base C. The number is mentioned as point f minus 1, f minus 2 up to f of minus m. To indicate that we are moving from decimal point on our right side, we have just used the notation minus 1 up to minus 1, and if it was on the left side representing an integer, this would be a positive number. So start with a base B representation. Initialize the value of the fraction f equal to 0.0 and set the index I equal to minus m. Then convert the fraction fi with base B to the equivalent value di with base C, again by using the table. The table is similar what we have used in the previous example. Now then update this value of fraction f by f plus d divided by b. So it's just opposite to what we had for the case of integer, and update the index from I to I plus 1. Repeat for all digits until I is equal to 0. That means from minus m up to, we just come to minus 1 and we finish at 0. Take an example. Convert the fraction 0.4 CD in hexadecimal to an equivalent value in base 10. We start with f equal to 0. Next, we read the value on the rightmost side, which is d, equivalent to 13. So 0 plus 13 divided by 16, we just convert it, and this is 0.8125. Then we read the next digit, which is c, add to this and again divide by 16, and we get the corresponding number. Finally, the last one is 4, and we divide another time by 16. So by repeated addition and division by 16, final value turns out to be 0.3000488. Notice here that you have a limited number of decimal digits in this case, and the accuracy would depend on how many digits are being used. We could truncate at certain position depending upon the availability of digits or register length in a particular processor, or in other case we can truncate as per the requirement of our own problem. The next example considers a conversion from calculator base C to base B, and it goes in the opposite direction. In this case, no division is required, and the process should be terminated when enough digits are generated. We start with fraction value f in base C, initialize I equal to 1, and put the value of b equal to f. Set d of minus I again with the operator which we get as a quotient, multiply v with b, and then correspondingly we get the value minus I, d minus I. The next value of v becomes b multiplied by v minus di, and convert di to f minus I using again the lookup table. We repeat this and set I index to the next value I plus 1 and repeat it till v is not equal to 0. Again an example, let us convert the decimal fraction 0.24 to base 2. So in this case we have c equal to 10 and the base b is equal to 2. We start with the value 0.24, which is our given value v, multiply it with base b, which is 2, and we get 0.48. And the left side, which is the integer, that represents now the coefficient, which is f minus 1 is equal to 0. Again, we multiply 0.482 another time with 0, we get 0.96. The integer part is again 0, so f minus 2 is 0. Another multiplication gives us 1.92. Now f minus 3 is 1. This process is repeated, and at the end 0.24 in decimal is equivalent to a binary fraction 0.00111 with base 2. And note that in this case we have a limited number of binary digits on the right side of the radix point, and that is 5. We could have gone on further, and theoretically there would be infinite accuracy, but that may not be required or may not be achievable with the finite number of bits in a register. Now, we have considered examples of positive numbers as yet, but computer would also be using negative numbers. The question is, how do we represent the negative numbers in calculations or for number crunching? There could be 4 different possible representations for negative numbers, or we could say combine positive and negative numbers together. The first representation could be a signed magnitude. So we could represent plus or minus along with the corresponding value of that particular number, which could be an integer or a fraction or a combination of the two. So plus minus, we say this is a signed magnitude representation. Now the second is the radix complement representation, and you are familiar with a common representation which is 2's complement. If we are dealing with binary numbers, this would correspond to 2's complement. And third option with us is the diminished radix representation, and that would be usually what we have as a base minus 1. So if our base was binary, it would be 1's complement, 2 minus 1, which is 1's complement. Of course, the diminished radix and the radix representation both are related to each other, and we could have conversion from one to the other. And the fourth representation is the biased representation. We'll discuss that in more detail later. Now, when we compare these first 3 representations, the sign magnitude has certain problems, and this might not be very convenient for computer calculations, or the CPU may not like it very much. To give you a simple example, if we have a 0, then it could be plus 0 and minus 0. We have 2 representations for 0. This would not be the case for 1's or 2's complement, and we will see some examples, simple numeric examples. Again, as I said, it might be a review for you, but still, till we go to the actual implementation of the arithmetic logic unit, understanding of these numbers, even if it is a repetition, is important, and you may just quickly go through these ideas. Let us have another example for representation of these negative numbers in the 3 representations which we have discussed in the next slides. Sign magnitude form is the simplest form for representing a signed number. A symbol representing the sign of the number is appended to the left of the number. This representation complicates the arithmetic operations. As an example, as we said, we could have in decimal plus 131, or we could have minus 131. The second representation the radix complement is the most common representation. Given an m-digit base b number x, the radix complement of x would be, we write it as xc is equal to b raised to power m minus x modulo b raised to power m. This representation makes the arithmetic operations much easier. The third example is the diminished radix complement representation, and this is with an m digit. The value of x would be, we write it as x c prime equal to b raised to power m minus 1 minus x. This complement is easier to compute than the radix complement. The two complement operations are interconvertible as xc equal to xc prime plus 1 modulo b raised to power m. You are quite familiar with 2's and 1's complement, and if 1's complement you just add 1 to it, it would become 2's complement, and vice versa. Now for some typical base, the table given in slide shows the complement representation of negative numbers. The radix and diminished radix complement is compared with each other. In the first row, number 0 in all cases would be represented as 0 except for diminished complement representation, where it could be 0 or it could be b raised to power m minus 1. Both are equivalent. Any number x for radix value or the diminished radix would be between 0 and b raised to power m divided by 2. So in fact, if we had 16 bits to represent a number, we just say that out of 16, the most significant bit would be indicating the sign. It would be 0 for positive and 1 for negative numbers. So the magnitude would correspond approximately to half the maximum representable value for 16 bits. That would mean actually 2 raised to power 15. That we'll see with another example. Now the next table shows the base 2 complement representation for 8 bits. So if we have 8-bit 2's complement, then the numbers which we could represent are positive values would be from 0 up to 127, and negative values would be from 1 minus 28 to minus 1. And correspondingly, if we consider 1's complement, then the positive number would be between 0 and 128, and the negative number would be maximum minus 127. Now there is a difference of 1 as we just saw, and mathematically we could write it as 255 minus magnitude of x. Now notice also that 0 in 1's complement is either a 0 or 255 would also represent a 0. Now the next table just shows the example of all the representations: 2's complement, 1's complement, signed magnitude, then as an example unsigned, and 16's complement, which is corresponding to hexadecimal. First row as an example is a positive number 27, and notice 2's, 1's, signed magnitude, unsigned, they are the same. For all these cases, the representation is 11011, which is equivalent decimal 27, and in hexadecimal it corresponds to 1b. Now next is a fraction 0.17. Again it is a positive fraction, and note all the values are same. So as a conclusion, for positive integers and positive fractions, it really doesn't matter which particular representation is used. All are equivalent. Now the next two examples correspond to the negative values. A negative integer minus 26. In 2's complement, this is 1, 0, 0, 1, 1, 0. Whereas in 1's complement, it is 1, 0, 0, 1, 0, 1, which is one binary less as compared to 2's complement. So in 1's complement, if you just add 1, it would become 2's complement. And then you just notice the sign magnitude. The first digit shows 1 as a sign digit, and the next 5 bits are exactly the same as 26 represented as positive. So this would be sign magnitude representation. Now there is no unsigned representation for this example. For negative numbers, you can't represent negative numbers for unsigned. And correspondingly, for 16's complement represented in hexadecimal, it is E6. So you could just consider as in hex 100 minus 26, that would be actually E6. The fraction minus 0.57 is in this case 2's complement, 1 point the remaining part, meaning that now this would be a fraction with 2's complement. And just notice again, in 1's complement there's only a difference of 1 in the least significant position. And so for the sign magnitude, we just have 1 representing as 1, 0, which would mean that the leftmost bit, the most significant bit, the leftmost would be representing a sign, and the remaining part would be magnitude. Shift right and shift left are two important operations of the arithmetic logic unit and could be used for various purposes. One typical example could be multiplication or division with base b. For example, if we have a binary number in a register and we shift it to left by 1 position, this would mean multiplication with 2. And on the other hand, if we shift the number by 1 position on the right, this would correspond to division by 2. This can be illustrated with a very simple example which we see in this slide. Let us see a multiplication of decimal 6 with decimal 4. In binary, 6 is represented using 5 bits as 0, 0, 1, 1, 0. And we want to multiply it with 4, which would mean let us shift twice this number on the left. So when we shift twice, this would become 1, 1 and 000, and that is equivalent to 24 in decimal. Now please note that we have used 5 bits to represent this number. Had we used only 4 bits, then the second shift would correspond to an overflow. So overflow could occur if we use 4 bits for this example, or if the number of bits are limited by the number of bits in the register, the overflow has to be taken care of. Similarly, if we divide 60 by 16, 60 represented in binary would be 0, 1, 1, 1, 1, 0, 0, and we need to divide it by 16, corresponds to shift right by 4 positions, and that would become 0, 0, 0, 0, 0, 1, 1 with a binary, and this fractional portion of the result would be lost, and we have only 3. So actually 60 divided by 16 would be 3 point something. So point something has been lost, and we have only the integer part as 3. Let us consider a couple of other examples with negative numbers and using the shift operations. Suppose we want to multiply minus 6 with 4. Minus 6 we represent as 2's complement using 5 bits as 1, 1, 0, 1, 0. Now let us shift it on left by 2 positions. When we shift by 2 positions, it becomes 0, 1, 0, 0, 0, which is equivalent to a positive decimal number 8, and obviously this is incorrect. What is the solution? Now let us use another bit. Instead of 5 bits, had we used 6 bits, then minus 6 would be 1, 1, 1, 0, 1, 0, and with 2 shifts it would be 1, 0, 1, 0, 0, which is minus 24. Conclusion, we must have enough number of bits so that with the shift on left, overflow does not give a change of sign. Another example for division, minus 24 divided by 2. So minus 24 again, in the case of 2's complement is 1, 0, 1, 0, 0. Shifting it right by 1 position gives us 0, 1, 0, 1, 0, 0, which is plus 20. So which is again incorrect. So we need to take care of the sign bit. So therefore, when we shift right and we see that the sign is changed, we had sign bit as 1, that should be copied as 1 and not as a 0. This is the familiar problem of sign extension which we have discussed earlier in our processor implementation. So copying the sign bit would now give us 1, 1, 0, 1, 0, 0, which is minus 12 decimal. Now you should note that changing the sign of bits in any particular number would correspond to also copying the sign bit. If it is a positive number, copy it as 0, and if it is a negative number, then you have a sign extension bit as 1. Take a very simple example. 24 represented with 6 bits would be 0, 1, 1, 0, 0, 0. If we use 8 bits for representing the same 24, just add up 2 zeros on the left side of this number, making this number as 0, 0, 1, 1, 0, 0. Same way, if we have minus 24 with 6-bit representation, it is 1, 0, 1, 0, 0, and if we extend it to 8 bits, then we should copy 2 ones on the left side, making this number as 1, 1, 1, 0, 1, 0, 0, which is minus 24 with 8 bits. This is a sign extension which we have been already using. After reviewing the representation of numbers both for positive and negative, let us now look at the arithmetic operations. The simple arithmetic operation to start with is the addition. Now we'll first consider the addition or arithmetic operations with unsigned integers, and then we will go to the signed integer and see the hardware implementation. As I said, the basic building blocks would be simple logic circuits consisting of AND gates, NOT and or exclusive OR gates. We will just see the implementation for different forms of adders, and then as a special case for subtraction, the same adder could be used. This slide shows the unsigned addition operation. The digit-wise procedure for adding m-digit base b numbers x and y is shown. We initialize digit j equal to 0 and the carry in to begin with, which is C0, is 0. Now we compute the j sum designated as Sj is equal to xj plus yj plus cj modulo b, and the carry for the next stage would be cj plus 1 within floors operator xj plus yj plus cj divided by b, which means the quotient corresponding to this division operation. We repeat this process with incremented index j is equal to j plus 1 and repeat till j is less than m, which is the number of digits that we have in our original number. A simple example for base 2 and base 16 is indicated in the next example. Just it's a conventional simple case of adding digit by digit, taking the carry to the next position and so on, and you are quite familiar with this particular addition process. We are still not taking into account the sign. It is unsigned integer addition. Now the hardware with this particular addition could be represented with just a square block. Xj and yj are the input to that stage, and cj is the input carry to that stage, and output sum is sj, and the corresponding carry is cj plus 1. So it is the jth stage implementation of addition of two numbers xj and yj with base b, and the implementation is just shown symbolically. Now let us look at the equivalent representation for binary numbers. For the binary number, if you look at only one stage, or we could say 1 bit ALU giving us the process of addition, and if we had half adder, it is indicated in the slide, and you see we need just one exclusive OR to give us a sum and an AND gate to give us a carry. And in this case, it's a half adder, no carry is coming from the previous stage. We have X and Y at the input. Now, the next implementation incorporates the previous carry as well. And you see there is one additional gate. So this would be a complete full adder with input X, Y, and the previous carry, which we just call in this case Cj, and next sum is Sj plus 1, and the carry is Cj plus 1. So we could further add up more stages and make it an m-bit adder with the stages either in cascade one after the other. Now this slide shows the cascading of different stages. So from the right side we have the least significant input, two numbers, two digits x0, y0, the carry is c0, result sum s0, and carry c1 is fed to the second stage, and so on. We have m stages. The last stage would give us a sum sm minus 1, and the carry would correspond to cm. The situation where the addition of two unsigned m-digit numbers result in m plus 1 digit number is called an overflow. Overflow is treated generally as an exception in some processors, and an overflow flag can be used to record the status of the result. We started today with the concepts of ALSU design, and we said for appropriate design we need to understand the corresponding representation of numbers. So we started with representation of numbers and saw how to convert the base from one to another, and then we saw different representations of negative numbers. We said in particular 2's complement for binary numbers, or the Radix complement, is quite a convenient representation and is frequently used for crunching these numbers. Then we just discussed how to add up two numbers without sign, unsigned numbers. We discussed half adder and full adder. For today, we'll stop at this point and would carry on next time with more further implementation of adders and subtractors, and then go on to the process of division and multiplication. For today, that's all. Allah Hafiz.